Established theory holds that distributed systems must synchronize state, coordinate behavior, and communicate reliably to functions. My dissertation shows that consistent decisions can emerge when none of these are possible. To explore this new paradigm, I'll walk through the challenges that classical distributed architectures face in the IoT environments and present core contributions that redefine how decentralized control can work without coordination. Let's start with a thought experiment. What if controllers in a decentralized IoT system could make consistent decisions without communicating with each other? The key insight is that they don't coordinate. They are informed by changes in their environment, autonomous agents with access only to their environment, yet they behave in agreement and operate in unison. Hello, my name is Rahav Dor. I developed this paradigm during my doctoral research at Washington University in St. Louis. If we can build this technology, we unlock dependable IoT applications that today seem out of reach, like smart homes that finally deliver on their promise, applications that let people age in place reliably and safely, agriculture IoT applications that make dependable decisions in their field without relying on cellular connectivity, helping grow more food to meet demand. In this talk, when I say control, I mean how the term is used in IoT, event-driven, discrete systems that sense, decide, and actuate, not continuous time, feedback-driven control theory. I'll focus on core ideas in this talk and use metaphors from bee behavior to illustrate mechanisms, though the theory's origins were not biologically inspired. IoT systems that require high reliability, like medical or industrial IoT, depend on distributed controllers to function. But classical distributed models assume strong connectivity, which rarely exists in IoT networks. The systems are interference prone because they operate in the physical world. The environment, intermittent and dynamic, is the norm for IoT applications. So I took a completely different approach. I began exploring what systems might emerge if agents act autonomously without coordination, but through their changes in their environment. Just as bees don't communicate to perform tasks, but respond to environmental cues. Controllers are privy to their environment through sensing and actuation, and these modifications may guide other controllers to make the same choices without direct communication. This principle is called stigmergy, indirect coordination through the environment. In social insects, stigmergy leads to highly resilient self-organizations, enabling task identification and individual contributions toward consistent task completion. In my architecture, the environment is what agents have learned over time and is fresh, like pheromone that decays over time. Because agents run the same logic in response to the same environmental cue, they arrive at consistent decisions without exchanging messages. In classical distributed systems, communication is required to prevent duplicate actions. A leader may issue a command ID and synchronize. However, in decentralized systems with network that may fail or partition, communication cannot be guaranteed. To enable high resiliency, we need multiple autonomous controllers that operate in parallel and execute tasks in unison. But without communication, they cannot coordinate to prevent redundant actions. This led me to develop the universal idempotent scheme, a coordination-free method that ensures devices act only once, even when multiple controllers independently generate commands. Instead of agreeing, for example, on a unique ID in advance, each controller independently derives the same value based on the task. in a similar ways, bees reacting to specific pheromone make the same decision without communication. That enables redundancy when needed and suppresses it once the task is complete. Consider the scenario. 3 controllers monitor a patient showing signs of respiratory distress. 2 controllers detect the event. The third is blocked by interference. The 2 functioning controllers running the same task generate the same command ID, ensuring the medication is delivered once. Additionally, resilience is enhanced because controllers are physically apart, so messages traverse the diverse path in all directions. In today's single controller system, that block controllers could mean the intervention is missed entirely. Take our hospital application further. If reliable telemetry and intervention are hard in hospitals, with high-grade equipment and managed networks, it is even harder to ensure safe, timely interventions after discharge to a smart home. We have had decades of smart home hype, but systems continue to frustrate users. Those systems are brittle because they run on an architectural model that has a fundamental mismatch with available infrastructure. In many IoT systems, automation runs on a single controller. If that controller fails or loses connectivity to a single device, the entire automation may fail. Even in multiple controller systems, current architecture assume that they can instantly transfer state to another controller, a process that can take seconds to minutes, and when the network topology is involved, even hours. Inevitably, such systems critically depend on the troublesome assumption that all devices are accessible from the current leader. To overcome these limitations, I designed a state transfer architecture that works through the environment, called control flux. Different steps of an automation can run on varying controllers at different times. So if one controller fails or is disconnected, another can pick up the task. This also localizes execution, which reduces latency, spreads load, and makes the system highly resilient by design. Our methodology spans the full spectrum of system research, beginning with conceptual insights, model formulation, followed by theory development and formal proofs, and extending through architectural design, implementation, and empirical validation. The theory was developed with general IoT applications in mind, and I implemented it and validated it in a smart home testbed. But its architectural principles are not domain-bound. I plan to expand its potential, and I hope that others will too. In environments like smart cities, industrial IoT, and intelligent agriculture, domains where interference is the norm. I opened with a question. What if controllers in a decentralized IoT systems could make consistent decisions without communicating with each other? This work answers this question. It introduces a new paradigm for dependable IoT systems our modern interconnected society relies on. Applications that operate in the real world, for and among people, where resources are limited and interference is the norm. This architecture is supported by rigorous mathematical proofs, ensuring it is formally sound. We validated it through more than 12,000 hours of simulations and 6 weeks of deployment, measuring reliability, fault recovery, and other key system properties. We have shown that the unimaginable is possible. Controllers that operate independently, work autonomously, and in parallel, yet act in unison, and provide consistency. Dependability doesn't come from engineering around reality, but from designing on top of scientific models that capture it.